All right, welcome. Today, we're going to solve a pretty cool chemical puzzle. We're going to uncover the secrets behind how molecules create all the vibrant colors we see every single day.
Okay, so let's dive right into this puzzle. We're starting with this chemical reaction, where one manganese complex, turns into another one. And just by swapping out its chemical partners, its color changes. It changes dramatically. So the big question is, why? What's going on here?
So to solve this mystery, we've got to gather some clues, right? Our first step, we're going to investigate the very heart of these molecules, that central manganese atom. We have to figure out if that's the thing that changed.
So the first most logical question you'd ask is, did the manganese atom itself actually change? And to figure that out, we need to find its charge, what we chemists call its oxidation state, in that first complex.
Okay, so we can totally calculate this, step by step. The key thing to remember is that the sum of the charges of all the little pieces has to equal the total charge of the whole molecule. You follow the math, and what do you get? The manganese has a charge of +2. Simple enough.
Now here's where it gets really interesting. When we do the exact same calculation for our second complex, the one with the cyanide partners, guess what? We find the exact same result.
So this is absolutely crucial. The manganese is in the +2 oxidation state in both molecules. The central atom is identical, and what does that mean? It means our explanation for why the color changed has to be somewhere else. The plot definitely thickens.
All right, let's move on to our next clue and see where this leads us. We need to look at our most important piece of evidence, how these two molecules actually interact with light.
So what you're looking at here is called an absorption spectrum. And honestly, it's like a fingerprint for a molecule. It shows us exactly which colors of light are being soaked up by each of our two mystery complexes. You can see them labeled A and B.
Okay, but wait a minute. How does absorbing certain colors of light lead to the color that we actually see? Well, the answer is this really beautiful bit of science, and it's all about what's there and what isn't. The secret, believe it or not, is the good old color wheel. The color a substance appears to be is what we call complementary. It's directly opposite to the color of light it absorbs the most. So what we're actually seeing is just the light that's left over. Okay, let's take a look at curve A from our spectrum. See that? It has its highest peak right around 470 nanometers. Now, if you check the color wheel, that falls smack dab in the blue-violet range. So if it's absorbing blue light, what color do you think we actually see? Yep, we look right across the color wheel and we find its opposite, orange. That means the complex for curve A is orange. And we can do the exact same thing for curve B. It's absorbing light most strongly in the green region. And what's the complementary color to green? Red. So compound B is red. And this brings us right to the core of our mystery. We know one is orange and one is red. But why? Why does just swapping out a chloride for a cyanide partner change which color of light the molecule decides to absorb? Well, the big aha moment comes from this really powerful idea called crystal field theory. And it is all about the electronic relationship between that central metal atom and its surrounding partners, which, by the way, we call ligands. Okay, so here's how it works. These ligands, they interact with the metal's electrons. Now, some ligands are weak field. Think of our chloride. And they only cause a tiny little split in the electron energy levels. Just a small energy gap. But then you have strong field ligands, like our cyanide, and they just forcefully shove those levels way far apart, creating a much, much larger energy gap. And this is the key connection, you guys. To make a jump across a really big energy gap, an electron needs to absorb a ton of energy. And that energy comes from high-energy light, like blue light. But to jump just a small gap, it only needs to absorb a little bit of energy, from low-energy light like green. So look at this. We now have all the pieces. We have the mystery of the color change, we have the forensic evidence from the spectrum, and we've got the theory to explain it all. I think it's time we definitively solve this case. All right, let's put it all together. The complex with that strong field cyanide ligand, it creates a huge energy gap. That means it has to absorb high-energy blue light, which is our curve A, and that's why it appears orange. Meanwhile, the complex with the weak field chloride ligand creates just a small gap. It only needs to absorb lower-energy green light. That's curve B, and so it appears red. Boom! Case closed. So the really crucial point here is that color isn't just some surface-level property. It's actually a direct measurement of the electronic structure deep inside a molecule. The color we see is literally a window into its quantum world.
And, while this whole investigation might have come from an exam question, the principle behind it is absolutely 100% fundamental to the world all around us.
I mean, this very theory is essential for creating everything from the vibrant pigments in our clothes and our paints to the contrast agents that doctors use in MRIs, and even the glowing phosphors that are making the screen you're watching right now light up. It even helps us understand how something like hemoglobin carries oxygen in your blood. It's everywhere.
So there you have it. We've turned a pretty complex question into a clear story, right? We went from a simple reaction all the way to a fundamental theory of matter. And hopefully this has sparked a little curiosity in you about the super colorful chemical world that is literally all around you,